Hello everyone, welcome back to our generator protection playlist. On this video we will talk about the loss of field protection ANSI 40 and under-excitation protection testing. So in this video we will explore how loss of excitation affects generator stability and system voltage, and how protection really detect and isolate such conditions. We will also go through the practical testing steps, including how to configure the distance or admittance-based characteristic, import and organize the raw data, and perform trip time characteristic verification using the advanced distance module. And by the end of this recording, you will have a clear understanding of both the theory behind the loss of field function and the hands-on testing process that ensures reliable generator protection. So let us get started. So in this slide, as you can see, we have the PQ plan, and we will introduce the concept of the loss of field protection, which is also known as under-excitation protection, with the ANSI code of 40. So when the excitation system of a synchronous generator fails or becomes unstable, the machine loses synchronism with the power system and starts operating asynchronously. In this state, the generator draws magnetizing current from the grid instead of supplying it, and causing overheating of both rotor and stator due to additional slip. For large generators, this condition can even lead to a system voltage collapse. Common causes include AVR mail operation, excitation circuit faults, or operating the generator with a leading or capacitive power factor. To prevent this, the minimum excitation limiter MEL plays a crucial role. It limits the generator's leading VAR intake and ensures that the field current doesn't drop too low. This helps to avoid entering the under-excitation region, where the generator becomes thermally and dynamically unstable. Overall, the LOF function, or loss of field function, coordinated with the AVR and MEL to protect both the generator and the power system from severe instability and potential damage. So as you can see from the PQ plan here is the reactive power into the system. So here is the overexcited region, and here is the underexcited region with the reactive power into the generator. And you can see here the stator and iron limits, and the stator winding limit with the rotor winding limit on the first quadrant. So in the first quadrant, the generator supplies megawatt and megavars into the system, which is called a normal overexcited operation. And on the fourth quadrant, the generator supplies a megawatt into the system, and the system supplies the megavars into the generator, which is called underexcited operation. And here is the MEL, which is called minimum excitation limiter. Now we will talk about the loss of field and under excitation PQ plan. And as you can see, we have here the different characteristic, which is called PSIG, and PSIG stands for pounds per square inch gauge, and it's measured by Newton over meter square. So it stands for pressure. And the PSIG stands for, as we called, pounds per square inch gauge, and it's a way to measure the pressure relative to the atmospheric pressures. In this context of a generator or turbine system, it refers to a pressure measured relative to the atmospheric pressure. So the PSI also stands for pounds per square inch, which is a unit of pressure. And here the gauge means the reading excludes the atmospheric pressure, which normally 14.7 psi at sea level. So for example, if the system reads 0 psig, the actual pressure is equal to atmospheric pressure. And if it reads 100 psig, which means the absolute pressure is 100 plus 14.7, which is equal to 114.7 psia. And also in the generator applications, the psig is commonly used to measure lubrication oil pressure, hydraulic or control oil pressure, steam or cooling system pressure. And accurate psig readings helps to ensure systems are operating within the safe and efficient limits. And here you can see the conversion from the PQ plan to the RX plan. Now we will talk about the effects. So when the generator loses the excitations, it starts behaving like an induction machine. So slip-induced eddy currents heats up the rotor surface, and the generator begins drawing high reactive current from the system, overloading the stator. So from the system side, this causes a loss of reactive power support and creates a reactive drain that can even trigger the voltage collapse. So to detect and to protect these conditions, two main methods are used. So we have two-zone offset Moho method, which is known as a GE method, and the other one, which called the impedance with directional unit, known as the Westinghouse method. So the impedance measurement method using the MHO or MOHO type distance relay is widely used and reliable approach for loss of field of protection. The relay operates in the fourth quadrant and is offset from the origin by about 50 to 75% of the direct axis transient reactance, which called X-D, to avoid misoperation during system disturbances. So in the two impedance element scheme, an inner and outer zones are used. So the inner element trips instantaneously for severe loss of field events, while the outer element includes a time delay to block stable swings. So this setup ensures both speed and security, especially in weak systems that cannot handle the generator reactive power demand. Also, the Westinghouse scheme on the right hand of the screen, or the impedance with directional logic, uses the impedance, directional, and undervoltage elements, so it assesses the system strength. So if the voltage drops, it assumes that the system cannot support the generator and trip with a minimal delay. But if the voltage remains, only an alarm is raised. In summary, the outer element should include a short delay to prevent a false trip, while the inner element can trip instantaneously or within a minimal delay of about 0.3 up to 0.4 seconds if stability is uncertain. Here is the impedance measurement using the distance protection MOHO. So using a distance relay of MOHO type is a widely applied reliable technique for providing the loss of protection or loss of field protection. So this relay characteristic must be set to the fourth quadrant as it's shown, and the relay must be connected to the machine terminal CTs and VTs with offset from the origin by 50 to 75% of the direct axis transient reactance, as we said. So X-D here to prevent the misoperation during the system disturbances. Also, a standard practice to set the impedance element for this type of scheme within a diameter of XD and offset of half of the XD as shown in the figure characteristic. So speaking about the generator parameters, as you can see, we have here the apparent power, which equal to 16 megavolt ampere. The nominal voltage of the generator equal to 5.3 kV. We have also the CT ratio, the VT ratio. Also, we have the XD 2.3 per unit, X-D 0.27 per unit, and many more parameter settings. So how to calculate generator parameters or two zones diameters and angles based on the relay generator parameters. Here we can, at first we can calculate the Z base, which is the base impedance of the generator, which equal to the kilovolt square divided by the apparent power. So 5.3 kilovolt square divided by 16 megavolt ampere will be equal to 1.755 ohm in primary values. So the Z base in secondary will equal to Z base in primary multiplied by the CT ratio and divided by the VT ratio, which will equal to 66.25 ohm. So the XD equal 2.3 per unit. So 2.3 multiplied by 66.25 ohm will equal to 152 ohm. X-D equal to 0.27 per unit, which means 17.9 ohm. Also X-D, which equal to 0.15 per unit, will equal to 9.94, almost 10 ohms. So based on the generator calculation, the relay calculation for the inner and the outer elements can be done. For example, for the inner element, the diameter will equal to 1 per unit. So 1 per unit means equal to Z base in secondary value. So the diameter will be 66 ohm, as you can see from here. So the reach will be 1 per unit, which is the diameter, and the offset will be X-D divided by 2, which equal to 9 ohm. And here is the trip time delay of the inner zone, which equal to 0.25 second. On the other hand, for the outer circle, so the offset is the same, X-D over 2, which means 9 ohm, and the reach will equal to XD, which is equal to 152 ohm as we calculate it. So here is also some consideration to be in our minds. So one of them is there is a problem to be considered, in which is the determination of the machine impedance because of the variation depending on the slip rate. So according to the values on the left, which is ZG equal to J multiplied by 2X-D can be assumed. And in practice, the loss of field impedance will not come to a single value as mentioned due to the variation of the quadrature axis reactance with the slip speed. So the locus look like an orbit around 2X-D. So when the relay operates based on the distance measurement, there is a drop in the operating voltage causes a smaller measured impedance, which can affect the accuracy and also requires converting the generator capability parameters into the impedance plan. So this process that adds complexity also. So however, With a numerical relay, which use the admittance-based characteristics, this issue are eliminated, and the admittance approach allows a direct and more accurate coordination with the generator operating limits. Additionally, the trip time of the static stability limit stage can be reduced when excitation voltage supervision confirms a true loss of field conditions. So typically, this supervision is set to 0.7 times multiplied by the load excitation voltage and divided by the voltage divider ratio. So you can see here the example of the relay parameter setting of Siemens 7UM62. Here is the under excitation protection, which is set to on. Here is a short time delay, which equal to 0.3 second, and start of excitation voltage supervision, it's enabled, and the backup of this voltage supervision is set to 2 volt. And you can see here the characteristic 1 and 2 and 3 in terms of the angles and time delay. So we have 3 time delay, we have 10 seconds for the characteristic 1, we have 5 seconds for characteristic 2, and 0.5 seconds for characteristic 3. Now we will talk about the admittance measurement advantages. So admittance measurement uses the positive sequence quantities to maintain a reliable performance and accuracy across a wide frequency range, typically 50 to 70 hertz on 60 hertz systems. This ensures the relay will not misoperate during power swings or system frequency variation. And the scheme often combines the advantages of both admittance and impedance methods for optimal coordination with the generator limits and protection. So we have zone 1 uses the offset MOHO element with a fast trip time to quickly respond to true loss of field events. Also, Z2 uses the impedance with the directional limit, as you can see, and also a slower time delay, aligning better with the generator capability curve and allowing the system to ride through a stable swing. Additionally, the voltage supervision can accelerate the Z2 tripping during the voltage collapse, especially when the generator starts importing reactive power and contributing to the system instability. Okay, so here is another example also of the parameter setting of protection relay. So we have the circle diameter equal to 50 ohm, we have the offset minus 10 ohm, we have the delay is 30, and the delay with a voltage control equal to 30 cycle. So let us explain all of this parameters. So in loss of field protection using the distance or the admittance characteristic, there is several key settings to define the relay behavior. One of them is the diameter. So the diameter represents the size of the circular characteristic in secondary ohms, determining how much impedance area is covered. Also, we have the offset, which defines how far this circle is shifted from the origin, also in secondary ohms, allowing a coordination with the generator reactance and stability limits and to avoid misoperation. Also, we have the voltage control. When enabled, the relay can use special delay with the voltage supervision. This alternate time delay activates when the positive sequence voltage drops below the set controlled threshold, ensuring that the relay reacts appropriately during the voltage collapse scenarios. Finally, the directional element is applied when the circle is placed above the origin, typically with an angle setting around 13 degrees to ensure a correct directionality and to prevent unwanted operation during power swings or external disturbances. So the parameter setting of this protection function can be taken directly from the power vector diagram or the admittance plan of the generator and entered in the protection device as a conductance values. Also, a conversion of this parameter setting to the impedance plan can be done, and there is a possible way to convert the configured parameter setting of the protection relay to be converted using an external Excel file. Also, you have to define the generator data. You have to define the tripping characteristic configured in the protection relay. Also, make sure that all the parameters set to secondary values. Then you can export or save the converted characteristic curve to a RAW file, and the RAW file is automatically saved to the folder of the used Excel tools. Then you can create this RAW file and you can use it in the OCC file. Here, we before starting the under excitation testing, first we can open the control center, the OCC file of the Test Universe software, and then we can use this data. So it's important also not to import the RAW file directly into the test object definition, since this would overwrite all previously entered data. Instead, we can use the organize features, as you can see. So this organize function from the file menu, this opens a dialog showing both the existing X-RAW and the RAW file. So from where highlight the appropriate distance function block and integrate it into the current test object from this button. So once done, you can simply click OK to exit and to save the updated OCC file, and this is safely merges the data without losing any previous setting. Okay, here is in this step we supplement the existing test object definition by adding the distance function. So since the tripping characteristic of the underexcitation will be tested using the advanced distance test module, to keep things organized, also it's recommended to rename this function to be underexcitation REU file, so it's easily distinguishable from other REU function. Also, you can set the line angle to 90 degree, as you can see from the system setting parameters here. So this line angle can be set to 90 degree, as the line length is not relevant in this case. Also, the voltage transformer should be connected to the generator output, while the current transformer on side 2 is grounded on the generator side. Also, be sure to apply the tolerance specified in the relay technical manual in the zone setting. And also for the local hardware configuration, we can map the 3 voltage output as a phase to neutral voltages. Also, we can assign a current system A S1 to minus L1, minus L2, minus L3, and the other current system P, which is S2 to be IL1, IL2, IL3 in this case. Also, we can map a binary input here as a trip command to complete the hardware setup. So here is the advanced distance module setting. So next we can move on to this module setting for testing the underexcitation protection. Start with the test model. So test model should be set to constant test voltage, and we can use the generator nominal voltage Vn as the test voltage, as you can see from here, the V test equal to 60.62 voltage. And also we have to make sure the maximum fault time, as you can see from here, which is 15 seconds, is configured longer than the highest expected trip time to ensure proper relay operation. So the maximum expected trip time is 10 seconds, so we can put it 15 seconds. Also, you can set both the pre-fault and the post-fault times, as you can see from the screen, to be longer than the ceiling time of the definite time over current protection. All other parameters can remain at the default values, and note that all subsequent tests are carried out as 3-phase faults only. Also, for the trigger position here, you can define the trip command as the main trigger condition. Additionally, also you can enable the reset, as you can see from here, the trigger options, and here is the auxiliary binary outputs. You can additionally enable the reset thermal replica to be continuously reset the thermal memory of the overload protection during the testing, and this ensures a consistent test result without accumulated thermal effects. So the first test here is to test the trip time. So now we will move on testing the trip times for the underexcitation protection. This is done using the shot test mode, as you can see from here. So where one test shot is defined in each zone of the distance characteristic. During testing, remember to consider the possibility of parallel tripping from the definite time over current, and also if there is any overlap or interference from this protection, make sure to adjust the test points accordingly to isolate the underexcitation response and to ensure accurate timing result. Okay, here is the second test, which is testing the characteristic. So now you can verify the characteristic of the underexcitation protection, as you can see from here, from the right hand screen of the impedance view. So in this test also you can use the shot test mode, and for each protection zone you can define one test shot, as you can see, at the minimum and the maximum tolerance line, and this approach helps you to confirm the relay's measured characteristic accurately and matches the expected zone limits to ensure both sensitivity and stability are within acceptable margin. At the end of the video, thank you for your attention and stay tuned for the next video.